Hello, welcome to another Andy's Workshop video. In my last video, I introduced you to my project, my kind of long-term project to build a process controller out of an old PC that I've got. The idea being that I could use this process controller to help in my home brewing efforts, where I would use it to control heaters, chillers, that kind of thing. And the first board that I built was this one, and you saw it in the last video. It has a bank of relays here and a triac here. These can all be individually controlled over a USB interface here. There's the USB to UART chip there, and an Atmega 328P here to do the actual firmware logic. Now with this built and functioning and tested, the next thing I needed to do obviously is to build a sensor board, because without inputs from sensors I have no knowledge, no way of knowing when to turn relays on and off and triacs and so on. So what I've done now is built a board that does temperature sensing. And the overall goal of this video is that I'll walk you through that board. I won't bother with the theory and the schematics and stuff. We'll focus on the practicalities of it and do some tests, and I'll explain why I made the choices that I did, and we'll run through it and we'll see what it looks like. So before I could do any kind of board design, I needed to choose a sensor technology for the kind of probe that I was going to use, this temperature sensor technology. There's quite a few to choose from, and the first one under consideration was the Thermocouple. You see them everywhere in Arduino projects. K-type thermocouples pretty much rule the roost for homebrew projects because they have a huge range of huge temperature range within which they'll work. They're not particularly accurate. The standard for a K-type is plus or minus 2.2, I believe, 2.2 degrees. But that's good enough for most projects, particularly the popular reflow oven type projects that people build with them. And they're easy to integrate with Arduino style projects, because you can get the little breakout boards for those Maxim integrated sensor ICs that you can get. So you see them all over the place. So I did consider the Thermocouple, and as an example, this is the one I use at the moment for my home brewing. It's a Therma 1T, which is a T-type thermocouple. It's more accurate than the K-type. This particular one comes with detachable probes that you can just plug in at the top here. If I put this in and switch it on, it comes on, and immediately it measures quickly, it reacts quickly to change. This particular one was calibrated by the manufacturer when I bought it less than a year ago, so I consider it to be accurate, and I use it as a reference to see how well the other probes that I've got are performing. It's nice. So if I were to use a thermocouple, I would probably use a T-type, because the range of plus or minus 1 degrees C, the standard range, is good enough for me. I'd prefer better if I could get it, but that's nice. And since this has been calibrated, I can trust it. But I do have to evaluate the other types of sensors that are available. So let's just take a look at what others that there are. So this sensor is a DS18B20. I think I've got that fully right. You'll know what I mean if you look on eBay. These sensors are really cheap. The whole thing cost about £2 or something like that on eBay. Very cheap indeed. Now the DS18B20 is an interesting type of sensor, because it doesn't rely on a cold junction or a resistance or anything at the end of the probe. It's completely integrated. It's a digital sensor, so the entire sensor, the sensing material, however it's done, I assume it's some kind of resistance sensor, is embedded in the DS18B20 IC itself, and the output at the other end of this cable is digital. It's a one-wire output. These have become quite popular in recent years because they're just so easy to integrate. There's no conversion technology required on the other end at your MCU. You just plug in the digital, just wire up the digital output here, and you can read it directly. It's very, very easy to integrate. And Dallas Semiconductor, who no longer exist, that's why it's DS, because it's Dallas were bought by Maxim, and assuming there hasn't been another round of integration in the and consolidation in the semiconductor industry, it probably still is Maxim. They've integrated the entire unit into this, and they claim accuracy of around, well, they claim sub 1 degree, which is very, very interesting. And I don't know how well these are calibrated. So I don't know how well I can trust these probes. That's the downside. And since I got it on eBay for about £2 and the whole thing's integrated in the end, I don't even know whether it's a real one. You know, it could well be a fake embedded in the end here. My experience with buying cheap Chinese probes, ICs off eBay, is that if it can be faked, it will be faked. So although this is an extremely compelling price, and it's actually sold at an extremely compelling price, and the claims of the accuracy are very good, I can't trust this enough to use it as much as I'd like to. And I didn't see any sources for integrated DS18B20 probes from reliable places. They only seem to be available on eBay. So as much as I like these things, I think I'll have to pass them by and choose a different technology. Right, next up we've got the resistance temperature sensors. Now this class of sensor relies on some kind of, relies on the fact that resistance changes with temperature. So then the different classes of probes, there are NTC and PTC thermistors. Those are available quite cheaply, they're not bad. And there are these probes, which are RTDs, resistance temperature detectors. And within these probes there are many different classes. This particular one is a PT100. From eBay. Well, it claims to be a PT100, of course, because it's from eBay and it's embedded and you can't verify that it actually is. I have no idea whether the resistance element in the end actually is platinum, because platinum, I would imagine, is not the cheapest material to source, and if it can be faked, it will be faked. So I don't know whether this one's real or not. But an RTD, if it is real, is the most accurate, and it's certainly the most repeatable, accurate and reliable and stable over the temperature range that you can get of all the sensors. The disadvantage to RTDs is the price. A good RTD probe and a good conversion, a good sensor, is not cheap indeed, but they are the best in the class. This particular probe is a 3-wire type. What that means is that you can see by the colour coding there's 2 blue and 1 red. The 2 blue ones are connected to the same end of the resistance element down here at the tip of the probe. The idea is there that you can cancel out the lead resistance by measuring the resistance across the 2 blues, because you need to do that, because the range of resistance that PT100 runs through is quite small, and just a small change in resistance can mean a big change in the actual temperature. And the red lead is connected to the other end of the probe. So basically the idea is to take a measurement, you run an excitation current through the resistance elements, and then you measure the resistance that comes back. So then you can convert it into a temperature. I decided to use RTDs. I'll jump straight to the conclusion here. Basically because of the accuracy, the fact that they don't need calibrating as often as thermocouples, and overall I know that these are the technologies used in industry. If you go to any professional outfit and you look at what they're using, it's going to be an RTD. By professional outfit, I mean a professional brewing outfit. Obviously, you know, different types of industry require different types of probes, but in the brewing industry, RTDs are the one to use. So with that in mind, I now need to design a board to be able to house these RTDs and read the sensor readings. Let's cut straight to the chase. Here's the board. I got this printed at Seed Studio in China, because at the time they were doing a $4.95 deal for 10 of these 10 by 10 centimetre boards, which was at the time was ridiculously good value. I think everybody's doing it now, but at the time they were the only ones. Just a quick run through as to what fits where, what I decided to do. You can house, you can affix 2 different RTD sensors here. They're both independently measurable. They're both 3-wire sensors. They run through some protection resistors here. There's a sensor, and then the sense resistor is positioned close to the IC that does the actual analog to digital conversion. The IC I chose was the Lineartech LTC2986. It's not a cheap sensing IC. It was about £25 plus VAT at Farnell. But Lineartech have a reputation for producing analog components that are of the finest quality. The datasheet's brilliant. They produce free software to allow you to verify your schematics, because this particular IC is not just suitable for RTDs, it will convert just about anything, and it will convert multiple sensors of just about anything. It's really something special. I did consider alternatives. There is a Maxim IC which will take an RTD input and convert it to digital. It's much cheaper than the linear tech, but I would needed two of them, which makes it a little less cheaper, but still it would have been a lot cheaper than the LT. But it was the quality of the datasheet and the software that comes with the LTC 2986 that swung it for me, and the fact that I know LT produced great stuff. So in come the sensors to the LT there. And then the output of that, you can see winging its way across to the footprint here, the DIP footprint for the Atmega 328. I've decided to use the Atmega 328P again because I used it in my last project for the board that does the relays and triacs, and simply because it worked. I have a few of them available. I don't need anything particularly powerful like an ARM. This will do nicely, and I can reuse much of the firmware that does the communication with the PC. It'll just be a copy and paste job. So here you've got the USB to UART converter IC. It's the same one as on the previous board, the microchip MCP 2221, if I remember correctly. Rumour has it it's actually a PIC, a hard-coded PIC. I never thought I'd actually code with a PIC, but unknowingly I've probably got one sitting in that footprint. Also worth noting on the board is this big footprint here for a Maxim, I think it's the Max 7221 if I get the number right. That's the driver for these two LEDs here. These are to constantly display the temperatures being read from the RTDs. So I'll have a constant display here. Even though this board's likely to be housed in a PC, well, it will be housed in a PC, I won't be able to see those when it's in the PC unless I cut a window in it or something, or run wires from these and mount it on the side of the case. Doesn't matter, very useful for testing to have a constant display there. So, anything else to mention? Yeah, some features of the board design. The ground plane here has a cut in it all the way down. So all the sensitive analog stuff that goes along here, the return currents go back to the USB connector which is there, and they do so without crossing the digital section where there'll be high-speed switching going on, which tends to cause noise in the ground returns. So the ground return from the digital is separated from the ground return from the analog side here. Also, the power supply for the LTC is one of LT's own ultra-low dropout, very low noise regulators. So it gets its own regulator, nice smooth power. It doesn't necessarily say in the datasheet that that's required. I think they do their own noise rejection, power supply noise rejection, when they generate the reference supply for the embedded analog digital converter inside there. But it doesn't hurt to have a good external supply for this thing. It's pretty much standard, easy to do, just a few pounds to put a different regulator on there. So okay, let's build this thing up and I'll show you it working. Right, here it is, all built up and sitting in a hard drive bay holder. The footprint, as before, is of a 2.5-inch hard disk. The mounting screws go in there in a little grid that you can see. I've just put screws in here ready to accept the spade connectors for the RTDs. Everything else looks nice. The little LED readouts sit on the edge there facing outward. I've codenamed these sensors as red and blue sensor. They're not coloured red or blue, it's just for identification purposes, because this is the red. This is a red LED and that's a blue one, so I'll be able to know from the red one, that one, blue one, that one. Easy to see at a glance, so you just don't get confused. I built this board up using my reflow oven. First of all, reflowed all the surface mount components, the sensor, the little discrete resistors and so on. That was not very exciting. It worked first time, which is good. And then I just sat down and did all the through-hole stuff around here for the digital side. Right, so the first thing I needed to do was to hook up the RTD that I got from eBay. So let's have a look at this thing. It's easy to verify whether the RTD that you've got is actually any good, just simply by measuring the resistance. Now, there are online, and I will put this, I'll link this into the video in a little picture-in-picture video, in-picture window a table of resistances to temperature. So you can just measure across the leads here and see whether the RTD is anywhere near what its nominal value should be, and whether it's going to need calibrating or not. So let's check out this one that I got from eBay. Okay, so let's have a look. Cheapo meter time. This is accurate enough. Let's switch it on. Wait for it to do stuff. Right, let's have a look firstly at what the lead resistance is. This will include the resistance of the probe leads and the multimeter leads. Let's see if I can get a good contact here. And it's thinking. We have about, of course, about 2 ohms. Bear that in mind. I can't null out the resistance on this cheapy meter, but it's just 2 ohms, you can remember that. Now let's have a look at what the probe is currently, what the resistance across the element, the PT100 element in the probe is 115.8. Right, so subtract the 2 ohms and we get about it's gone down, about 113.5 ohms. Now if I have a look at the resistance temperature versus resistance table, 113 ohms is apparently 35 degrees centigrade. I can tell you it's not 35 degrees centigrade in here. It's a nice comfortable 19 degrees centigrade. Now for that probe to be correct, it would need to be reading around 107 ohms. So to be fair, it's miles off, which is not really that unexpected for an eBay probe. It's my worry, of course, is that it's not a PT100. It could be goodness knows what embedded in the end of that probe. Now, obviously, the good news is that a constant offset like this can be calibrated out. That's no problem. I can do that. What I worry about is the linearity of it, and given how far off it is from nominal, whether it will actually track the changes in temperature versus resistance as a PT100 should, and whether it's, basically it's a worry. So I don't think I'll be using this as my first choice probe, not by a long shot. So, of course, that's not the only probe available. I'll just reach over here and get the one that I bought that actually cost a few more pounds than the one on eBay. This, I can just about fit it in, is a 25 centimetre probe from a company called Thermocouple. This one is much better. I know it's a good one. It costs about £22 with delivery. That's not ridiculous for an RTD. Just look online and you see how expensive good quality probes are. This one is definitely much better. It's used by a professional brewer that I know of, and he didn't even bother calibrating it. It was straight off the mark. Now I've crimped on some those loop terminals that you get on the end, and if you look at these, let's do a measurement across the resistor. And that's much better. So you've got 110 ohms, subtract the 2 and a bit that we have for the lead resistance, and you're down to near as damn it what it actually is in this room. So I have a much higher confidence level for the professional probe. This is definitely a PT100. A company like Thermocouple wouldn't risk their reputation by selling something that just isn't what it claims to be, because they are used in industry. So this is the one that I will actually use, and I will use it to calibrate the dodgy ones that I get from eBay. I'll calibrate them, and I'll attach the eBay ones side by side with this good probe, and I'll see how it changes with temperature, just to see if the eBay one does respond with the same linearity as the professional probe. And if it does, then there's no reason why I can't use it. I can dial in the constant calibration value that's required, and knowing that it's going to respond the same way as a professional one. But to start with, I'm going to use the good one. Right, let's switch this thing on and see some readings. Right, here it is, switched on, looking good. So you can see the red connector here is connected to my good quality RTD. The blue one is connected to the eBay one. I've programmed the firmware to apply correct calibration values so that the temperature matches my Thermo 1T, which I know is calibrated by the manufacturer. So they're pretty much matching each other now. They'll drift, obviously. They'll show slightly different values as the the temperature changes in this room. The output from the LTC 2986, I've run this for many hours actually before I filmed this. It's completely stable. It doesn't ever give erroneous readings. It doesn't jump around. It's very, very stable indeed. Very good quality IC, and I do like it. It does actually tell you whether it encounters an error during the reading, and if that happens, then my firmware will display error on here, and also in the readings sent back to the PC, there's a field that says that whether the reading is an error or not, and if so, what type of error you've got. Rest of the board looks very similar to the switching IC. These are status outputs for the UART, which tells you whether there's any traffic going through it, the UART to USB converter, power LED over there, and there's, just because I had space on the board, I put an alert LED down here, which I can flash. I'll show you that, because it's just so exciting, isn't it, to see an LED flashing. Look, there you go. Isn't it wonderful? That's just so I can display any kind of problem indicator, if that LED would even be visible from within inside a PC case. I'll switch it off before it annoys anybody. There, gone. Okay, so basically I've got what I want. The readings are stable. I can calibrate them to match reality, and over time I'll be keeping an eye on whether this eBay one actually tracks the same temperature, whether the calibration needs adjusting over time, and whether it actually works over a period without drifting, that kind of thing, the things you don't want out of a temperature sensor. So that's it, that's good. I'm really pleased with what I've got. I'm just wondering, can you actually see those LED readouts there, just so you can see them better? They always look better if you look at them through a filter like that. You can see they're both very similar to each other. To the naked eye, those are easily visible. They just look like bright LED readouts from a clock or something. But for some reason, they never film well. I don't know why, but you have to put them through a dimming filter like that to show them off, looking good. But anyway, before I digressed, I think I'm done with this video. I've shown you what this can do. And there's a full write-up on my website. The website's got the schematic, it's got the documentation for the build process, it's got the full bill of materials. You can build one of these boards yourself if you want. The Gerbers are there for you to download. The firmware is available from GitHub in a ready to flash hex file, so you can just flash it straight onto the Atmega 328 using the ISP header there. That's a standard pin out for the USB ASP devices. And the next thing I'm going to do is, well, I have to install these inside my spare PC, and I have to get writing some some controller software, because the next level up the stack, if you like, this is the hardware build, it's done. You move up the stack in terms of the overall system design. Next level up is the controller that will orchestrate receiving commands from a user interface, whatever that may be. It will translate those commands into commands to the firmware to make switching decisions, and it will receive streaming temperature readings back up so that it can make an informed decision. So that's the kind of middleware, and that's what's going to get written next. And since I got a powerful PC to run this middleware, I can use a nice high-level language to save me an awful lot of time and effort, and hopefully I can just build something nice and quickly. But that's the next stage. For now, I'll be signing off, and I hope you've enjoyed this video, and please visit my website if you want to get the firmware, all the stuff that I talked about before. It's all there, it's all free, and that's it. So have a good day.